I read an article tonight. It seemed to align with some of the concepts in the MICT theory. After some exploration, the paper above reinforces the MICT theory and the applied concepts of human quantum cognition. Gemini states we haven't explicitly stated this is a goal of our work. This Gemini session doesn't know about all of our earlier conversations. The following is our new project, the MICT-based cognitive model. That is some awesome stuff we've covered tonight. More to work on, LOL. From our work and what we've been discussing, can we make a MICT-based model of human thought or cognitive processes? I have other references around the subject. We might be able to get some things we need to complete too. Foundational Principles, MICT, and Cognitive Science. Our model will be based on the following core principles. MICT cycle as the fundamental unit, the MICT cycle, mapping, iteration, checking, transformation, will be the fundamental unit of cognitive processing. This means that we'll view all cognitive processes, perception, attention, memory, reasoning, decision-making, language, etc., as iterative cycles of information processing. Hierarchical organization. Cognitive processes will be organized hierarchically with multiple MICT cycles operating at different levels of abstraction and interacting with each other. This aligns with the infinity ladder concept and with the known hierarchical structure of the brain. Interconnectedness. Different cognitive processes and their corresponding MICT cycles will be interconnected, sharing information and influencing each other. This reflects the highly interconnected nature of the brain. Adaptability and learning. The MICT framework inherently supports adaptability and learning. The transformation stage allows the system to modify its internal state and behavior based on experience and feedback. Context dependence. Cognitive processes are context dependent. The MICT framework, with its explicit mapping stage, can incorporate contextual information into the processing cycle. Probabilistic reasoning, HQC. We can incorporate principles of human quantum cognition, HQC, to model the probabilistic and often non-classical nature of human thought. Components of the model. We'll need to define the key components of the model and how they relate to the MICT cycle. Here's a proposed structure drawing on established concepts in cognitive science and neuroscience. Sensory input, mapping. This is the input to the system. It represents information from the external world through the senses and from internal bodily states. The MICT connection. This is part of the mapping stage. The system maps the raw sensory data into a more structured representation. Components, sensory receptors, model the different sensory modalities: vision, hearing, touch, smell, taste. Feature extraction. Model the initial processing of sensory information, for example, edge detection in vision, frequency analysis in hearing. Perceptual organization. Model how the brain groups sensory features into coherent objects and events. Working memory, iteration and checking. This is a short-term memory system that holds and manipulates information that is currently being processed. It's like the RAM of the brain. MICT connection. Working memory is crucially involved in the iteration and checking stages. It's where we actively process information, perform calculations, make decisions, and evaluate outcomes. Components. Phonological loop stores and manipulates verbal information. Visuospatial sketchpad stores and manipulates visual and spatial information. Central executive controls the flow of information and allocates attention. Episodic buffer integrates different types. Long-term memory, mapping and transformation. This is a long-term storage system for knowledge, skills, and experiences. MICT connection. Long-term memory is involved in both the mapping and transformation stages. Mapping. We use our existing knowledge to interpret new information. Top-down processing. Transformation. New experiences can modify our long-term memories. Learning. Components. Declarative memory for facts and events. Semantic and episodic memory. Procedural memory, memory for skills and habits. Emotional memory for emotionally significant events. Attention, mapping and checking. This is the mechanism for selecting which information to focus on. It acts as a filter and a prioritizer. MICT connection. Attention is crucial for both mapping, selecting relevant information from the environment, and checking, focusing on specific aspects of the current state. Components, selective attention, focusing on a specific stimulus or task. Divided attention, attending to multiple stimuli or tasks simultaneously. Sustained attention, maintaining focus over time. Executive functions, iteration and transformation. These are higher-level cognitive processes that control and coordinate other cognitive functions. MICT-Connection. Executive functions are involved in all stages of the MICT cycle, but particularly in iteration, planning and executing actions, and transformation, adapting strategies and learning. Components, planning, setting goals and developing strategies to achieve them. Decision-making, evaluating options and making choices. Problem-solving, finding solutions to novel or complex problems. Working memory, as described above. Inhibition, suppressing irrelevant information or impulses. Cognitive flexibility, shifting between different tasks or mental sets. Language processing, mapping, iteration, checking, transformation. This is a specialized system for understanding and producing language. MICT-Connection language processing can be modeled as a complex interplay of MICT cycles involving mapping, parsing the sounds or letters of language into words and sentences, iteration, building a representation of the meaning of the sentence, checking, verifying the grammatical correctness and semantic coherence of the sentence, transformation, generating a response or integrating the meaning into the current context. Emotion, mapping, checking, transformation. Emotions play a significant role in the mapping and iteration of tasks. MICT cycles can be applied to various cognitive processes. Let's take a look at some examples. For perception, like seeing an object, mapping involves sensory receptors receiving light from the object. Features such as edges, colors, and shapes are extracted. Iteration is where the brain compares these extracted features to stored representations of objects in long-term memory. Checking happens when the brain evaluates the match between the perceived features and the stored representations. Finally, transformation occurs when the object is recognized, categorized, and labeled. The internal representation of the object is updated. Now, consider problem solving, like solving a math problem. Mapping starts with reading and understanding the problem statement. You identify the knowns and unknowns and represent the problem mathematically. Iteration involves applying different problem-solving strategies, such as working backwards, using analogies, or breaking the problem down into smaller parts. Checking is where you evaluate each step of the solution process and check for errors in calculations or reasoning. Transformation is when you arrive at a solution and update your understanding of the problem-solving strategy. Lastly, decision-making, like choosing what to eat. Mapping means assessing your hunger level, available food options, dietary restrictions, and preferences. Iteration involves considering different food options and their potential consequences, like taste, health, and cost. Checking is evaluating the options based on your criteria. Transformation happens when you make a decision and eat the chosen food, then update your preferences based on the experience. So, as you can see, MICT cycles provide a structured way to understand various cognitive processes. Hierarchical structure, example. You could have a hierarchy of MICT cycles like this. Low-level sensory processing, like edge detection in vision. Mid-level object recognition, language, parsing, and motor control. High-level problem-solving, decision-making, and planning. Meta-level monitoring and controlling the overall cognitive system, such as executive functions and metacognition. This could be a meta-MICT cycle. Implementation computational model. You could implement this model as a computer simulation using a programming language like Python with libraries like NumPy, SciPy, and potentially TensorFlow or PyTorch for neural network components. Agent-based modeling. You could use agent-based modeling techniques to simulate the interactions of multiple MICT cycles, neural networks. You could use neural networks to implement some of the specific cognitive functions like pattern recognition and decision-making. Symbolic AI. You could combine neural networks with symbolic AI techniques such as knowledge representation and logical reasoning to create a hybrid system. Jarvits, as an implementation, Jarvits can be seen as a specific implementation of this general cognitive architecture. Connecting to existing cognitive models. Your MICT-based model has connections to many existing cognitive models and theories, including AITR, a cognitive architecture that emphasizes production rules and symbolic processing. SAW, another cognitive architecture that focuses on problem-solving and learning. Connectionist models or neural networks. Your model can incorporate neural networks as components within the MICT cycle. Bayesian models of cognition. Your model can incorporate Bayesian inference for probabilistic reasoning. Dual process theories. The distinction between fast, intuitive, and slow, deliberate thinking can be mapped onto different types of MICT cycles. Global workspace theory. The idea of a global workspace where information is broadcast to different cognitive modules aligns with the interconnectedness of MICT cycles. Applications: AI development, building more human-like AI systems; cognitive science, understanding human cognition; education, designing more effective learning environments; brain-computer interfaces, developing interfaces that can interact with the brain in a more natural and intuitive way; understanding consciousness, potentially shedding light on the nature of consciousness. Actionable steps: literature review. Conduct a thorough literature review of existing cognitive architectures and models of human cognition. This will help you understand the current state of the art and identify areas where your MICT-based model can make a unique contribution. Choose a specific cognitive function. Start by focusing on modeling a specific cognitive function, like perception, decision-making, or language understanding, using the MICT framework. Don't try to model everything at once. Develop a computational model. Implement your model as a computer simulation. Test and refine. Test your model against empirical data, such as data from psychological experiments, and refine it based on the results. Gradually increase complexity. Gradually increase the complexity of your model, adding more components and features as you go. Connect to Jarvits. As you develop your model, consider how it can be integrated into Jarvits. By systematically applying the MICT framework and drawing on existing knowledge in cognitive science and neuroscience, you can create a powerful and insightful model of human thought. This is a long-term project, but it has the potential to significantly advance our understanding of the human mind and to lead to the development of more human-like AI systems. The key is to start with a well-defined scope, build incrementally, and continuously test and refine your model based on empirical data and theoretical insights.